Hi, everyone. Welcome to the AGU College of Fellows Distinguished Lecture Series 2025-2026. My name is Julio Cañón. I am a professor at the Universidad de Antioquia in Medellin, Colombia, and we are very proud to host for the fifth time on this series a lecture today, which is intended for young researchers and students to engage in earth science and studies around the world. We hope this lecture will be shared through our streaming in YouTube at the Universidad de Antioquia. So it could be recorded. It would be recorded for people to see or to watch this conference later as well. And today in particular, we are very proud to have Professor Wen Li. She is a professor in the School of Geographical Sciences and Urban Planning at Arizona State University, where she directs the Spatial Analysis Research Center and the Cyber Infrastructure and Computational Intelligence Lab. Her research interests include cyber infrastructure, big data, geospatial artificial intelligence, and their applications in data and computation-intensive environmental and social sciences. Her work has led to widely used cyber infrastructure tools and conceptual advances that support climate resilience, disaster response, humanitarian aid, and clean water access in underserved communities. Dr. Lee holds a bachelor's in computer science, a PhD in Earth System and Geoinformation Science, and completed her postdoctoral training in geography. She has been the recipient of multiple awards and recognitions with over 120 journal articles published in leading disciplinary outlets. Her interdisciplinary background informs a research agenda in earth science informatics that is both methodologically innovative and societally impactful. Today, Dr. Lee will be talking about the use of artificial intelligence to advance earth science in the future, all the opportunities and challenges that we face on the use of these technologies. And we are very happy to have you here today, Dr. Lee. Welcome.
Thank you, Dr. Kanan. Thank you for the invitation and thank you for having me. Good afternoon, everyone. It's a great honor for me to represent AGU College of Fellows Distinguished Lecture Series to share my research with colleagues at Universidad de Antioquia. I apologize for my pronunciation. I'm a computer scientist by training, and I have always been fascinated by how we can use informatics to tackle earth science challenges. And today I will be sharing some of my team's recent research in big data, cyber infrastructure, and AI, especially geo AI. And I will discuss how these innovations could help manage big Earth observation data and also accelerate scientific discovery and generate societal impact. So since joining ASU, Arizona State University in 2012, my team has been dedicating our efforts in developing this cyber knowledge infrastructure, which is a knowledge-driven data infrastructure addressing the challenges in the entire data lifecycle, from data sharing to the discovery of distributed geospatial data, to the intelligent search of data of our most needed data set, and also to the integration of diverse dataset and the visualization and the real-time visualization of geospatial big data, as well as the intelligent analytics of the data. And the GeoAI serves as the intelligence core that power up all the elements in this data to knowledge production pipeline. So what is GeoAI? In a nutshell, GeoAI is a combination of geospatial sciences and AI. It includes application of AI methods for solving geospatial problems, and it's also about the integration of geospatial domain knowledge and the spatial principles to guide the design of better AI models. So it is a two-way street here, with knowledge transfer from AI to geo and also from geo to AI. And GeoAI evolves as its three-pillar technology evolve. First, the proliferation of geospatial big data like satellite remote sensing imagery, the data from numerical simulation models, and social media posts, as well as the real-time sensor observation data monitoring the operation of smart cities. So these big geospatial data offers ample opportunities for us to ask new questions and also make new discoveries. And the other two enabling technologies of GeoAI, of course, include AI and its revolutionary development in deep learning, as well as the rapid advances in computing technologies. So you might be wondering, what is a geo in GeoAI? And the geo can refer to geospatial applications, like when we use AI for different mapping tasks, like crop mapping, disaster mapping, mapping land use and land cover change, mapping Arctic permafrost thaw, and even mapping our built environment, such as infrastructure. And this image on the right shows a Sentinel-2 image captured in Sydney in March 2021. And you can see there is a significant flood in an urban area. And in this scenario, GeoAI can help us accurately map the flood extent to support the disaster response effort. And the geo in GeoAI can also mean advanced AI methods custom designed for geospatial data analysis. And one of such example is NASA and IBM's Geospatial Foundation model, PRISVI, which is a large model trained on a huge amount of Earth observation data. And once it's well trained, it can be adapted to support a wide range of downstream applications, like those listed in this figure. And the emergence of GeoAI as an interdisciplinary field requires the interlocks of the two fields, Geo for AI and also AI for Geo. And my particular interest in GeoAI is to leverage it to address critical environmental challenges because environmental change is threatening every corner of the world. And in Maricopa County, Arizona, where I live, the heat-related death has become a major public health concern. And in 2023, more than 600 heat-related deaths were reported. And this is over 52% increase from just a year ago. And the environmental change is also threatening critical infrastructure. And this animation, put together by Dr. Higman, shows a landslide hazard near Alaska. As you can see, the slowly moving landslide are forcing an Alaska highway to move. And this image is from Planet Labs, and it spans from 2016 to 2023, so it's pretty recent. And it won't take too long to overtake it again. And here is a higher resolution view of the same areas. So this is from super high resolution commercial satellite imagery Maxar, also taken in 2023. So we can see the new highway and also the large landslide, which is also very deep. It's about 30 meters from the surface to the shear plane. And this line next to the highway is a Trans-Alaska oil pipeline. It's a major oil pipeline that is also at risk from this landslide. So this hazard is really raising serious concerns about the critical infrastructure. And switching from nature to communities, here is a drone image taken just a couple months ago of an Alaska community. And the climate change and Arctic warming has caused the frozen ground to thaw, and it has caused a lot of damages. As you can see, the rocks protecting the riverbanks are sliding into the water, and so are the buildings. So many Arctic communities are being forced to relocate the entire village because of permafrost thaw. And these examples show that the climate change isn't just affecting the environment, it's also threatening critical infrastructure and have serious impact on humans. And there is an urgent need to address these challenges. Dr. Don Wright, who's the member of National Academy of Sciences and also chief scientist from Esri, the largest geospatial company in the US, has called out new capabilities to achieve continuous and near real-time mapping and monitoring of the Earth's surface, so we can better cope with the climate change on a global scale. And the GeoAI can help us navigate this. For example, to address the extreme heat, GeoAI can map mobile homes to identify vulnerable communities so we can help the relief expert to deploy cooling resources more effectively. And GeoAI can also provide near real-time monitoring of the evolving situations like a landslide. And using GeoAI, we can also monitor the permafrost thaw and predict where future thaw might occur. And this will help the Arctic communities, especially the indigenous community, to develop climate adaptation plans, including relocating the entire village they are often forced to make. So in the past decade, my team has developed an extensive research program in GeoAI for environmental mapping. And it started from a US Geological Survey funded project to map simple meteor craters in Arizona. And that's just one type of natural features we are mapping. And later, we expanded our GeoAI research to map multiple natural features like ridges and valleys across the entire US. And then after that, we took GeoAI beyond Earth and did a space application. So we applied it to map craters on the global Martian surface. And then we returned to Earth and focused on a very special region, the Arctic, using GeoAI to map permafrost thaw in near real time. And in recent years, we've continued to address broader societal challenges, supporting risk assessment and also disaster response by mapping different kinds of disasters like wildfire, landslide, and floods. And this diagram actually shows how our research has evolved from a smaller project, just lab-based research, to larger collaborative projects that build problem-driven GeoAI solutions for societal impact. And next, I will introduce you two recent projects where I collaborated with interdisciplinary teams to use GeoAI to monitor environmental changes and also respond to emerging crises. And one project involves expanding the Permafrost Discovery Gateway, which is an online tool for creating and exploring big data to support science and also help Arctic communities to tackle real-world challenges. And this project was originally funded by the National Science Foundation of the US and more recently by Google.org. And this is led by the Woodwell Climate Research Center and international collaborations among 7 organizations. And with the support from Google, we aim to use GeoAI to track permafrost thaw in near real time to support climate actions. And our team has built a big data creation workflow that leverages super high resolution satellite imagery and high performance computing facilities. So most of them are actually funded by the National Science Foundation. And using this approach, as well as the GeoAI, to foster the creation of big permafrost data at the pan-Arctic scale. And my team's focus is to develop new GeoAI models that not only allows high resolution and large scale mapping, but also a model that can create high quality products, capturing permafrost thaw more accurately. And for example, one of the thaw features we're mapping is called retrogressive thaw slumps. It's a type of landslide that forms when permafrost causes the ground to collapse. And these features are very important indicators of Arctic warming, but we currently do not have detailed information about where they are occurring across the Arctic and how they are changing. So I will be a little bit technical here. So to generate this critical scientific information about permafrost thaw, we leverage approach called the multimodal GeoAI for mapping the thaw slumps. And multimodal refers to using data from different sensors to capture various type of information. And they are actually complementary data sources, and when combined together, will provide a much more comprehensive view about the study area. And our model is based on an encoder and decoder architecture. Each data modality will go through its own data processing pipeline. And when the feature map is extracted, they will be fused strategically together and then send it to the downstream segmentation tasks. So the output will be telling us where the retrogressive cell slum are located and how large and what's the shape of it. And we first experimented with data from various sources and also modalities, including the optical image. As you can see here, in the arrow pointed area, there is a dent, and this dent is a retrogressive cell slums. And we have also used NDVI data from Sentinel-2. So NDVI refers to normalized difference vegetation index. So basically, it's a vegetation index. The higher the value is, like the greener, when you see on the image, that means there are more vegetation covers. And we have also introduced the digital elevation data, which we can use to capture the elevation changes between the salt slums and also their surroundings. And these data are pre-processed to ensure alignment in both spatial resolution and also geolocations. And this table shows the RTS mapping result using different modalities and also fusion strategies. So as you can see here, if we use the RGB image alone, then we can only achieve a prediction accuracy at about 40%, which is quite low. And when we add additional data modality like NDVI, then the model's prediction increased to over 40%. And this result highlights that multimodal learning is very helpful, but not all modality contributed equally. So as you can see here, after we further adding DEM to the model, the prediction accuracy actually drops a little bit. So when we look closer at the data, so as you can see here, within the orange box, on the optical image, there are the salt slum feature. But at the corresponding location of the DEM data, we can hardly observe this dent. So we believe there may be some temporal misalignment between these two data modalities that has caused the significant challenge in the effectiveness of this data source. And besides introducing multimodality data, we have also introduced the data fusion strategies. And a lot of these prior approach, when you have multiple data source or multi-modality data, is to use channel expansion. Like I have RGB optical image, and if I have additional data layers, I just stack them together to make, it's also called a channel expansion. So to make the input pretty fat. And another like more feature level fusion approach is once we generated the feature map, we will use a kind of a fusion approach called a convolutional fusion. And in our methods, to better utilize the different modalities, we propose a residual cross-modality attention fusion. So basically, the strategy is we know optical image is the most effective, and then we has fuse optical image with other modalities. And then after that, we will combine them together. So this is kind of a hierarchical fusion strategy using other data modality to enhance the feature representation within the optical image to get the better result. So here we combined we compare the different fusion methods, including data level fusion, which I have just showed you called the channel expansion, and also feature level fusion of different approach. So the last line shows our proposed data fusion approach. And you can also see these are the different input modalities. So as I mentioned earlier, because we found the DEM is not very effective, so we replace DEM with another data layer called the near infrared band. And because near infrared band can also help to capture vegetation and soil moisture. So that turns out to be a very effective strategy when we combine multimodality data and also with our proposed fusion strategy. And here are some of the visualization results. You can see this is the ground truth data, which the red regions are where the RTS are located, and they are actually annotated by domain expert of South Slum expert. And this image is actually located in Baffin Bay near the coast of Greenland. And the other three images are the model prediction result. So as we can see, if we use optical image alone, the model is only able to predict one of these four salt slums. And when we are adding additional data modality and using our proposed fusion strategy, we can see that the model's prediction get much improved. But again, because the detection of salt slum is a very challenging problem, so even with the current modeling approach, for this image, we are still missing one prediction. And as for the next step, we are going to apply this model on our workflow to conduct the pan-Arctic high quality and high resolution mapping of Arctic permafrost soil. And these red dots show the current sample locations for model training, for the AI model training. And we are now building a much larger data set that is representative of the heterogeneous Arctic landscape. And we are also taking our research up to the next level. So besides answering the question of what is happening now, and we are also developing seasonal forecasting models to predict where and when future thaw might occur. So one reason this research resonated with me so well is because it gives my work some real meaning. The information we are generating about permafrost thaw is being used by the Arctic communities to create urgent climate adaptation plans. And in some cases, this means relocating the entire village to address the devastating effects of the permafrost thaw on infrastructure and also on daily lives. And we're also using this information to inform climate policy and motivate climate action, and both domestically and also internationally. So as shown in this photo is Dr. Sue Natalie testifying before the U.S. House of Representatives about the impact of permafrost thaw and the needs for new policies and adaptation plans to help sustain the Arctic communities. And this is also where real-world impact of GeoAI is demonstrated. And now, if we switch the gear from the Arctic to the dense urban areas, I will show you some of our recent efforts in building a GeoAI solution to support the disaster response and humanitarian aid. And this is a very different types of GeoAI technique than the one we used for the Arctic, which focuses on analysis of image data. And in this effort, we aim to build an open knowledge graph to support fast forward decision making. And we achieve this by linking and integrating cross-domain data, and it mainly handles semi-structured and unstructured textual data. And what we emphasize in this graph solution is the relationships between different data sets. And this knowledge graph we built is called the Nowhere graph. And currently it has over 27 billion of location-related facts. And it's arguably one of the largest open spatial knowledge graph that has been published today. And Nowhere Graph is a project funded by the NSF Convergence Accelerator Program, and it involves 4 PI institutions and a partnership with over 10 organizations from multiple sectors. And our goal here is to build an open and densely integrated knowledge graph to tackle the most critical challenges at the human and environment nexus. And Nowhere Graph stands out with several unique features compared to other graph solutions. So first, we aim to enable it to know by linking and integrating cross-domain data, information, and knowledge. And it's also designed to quickly assemble real-time data for evolving situations like disasters. And the second feature is to know where. By using location as a key to link across domain data, it's specifically tailored to answer spatial queries and spatial reasoning. And finally, we're also developing web-based decision-making tools to help to provide location intelligence to help our graph users to make more informed decisions. And my team at ASU has been leading the development of geo-visualization tools and a part of the graph to support disaster response and humanitarian aid. And what we are partnering with a nonprofit organization called the Direct Relief. It's a humanitarian organization focused on providing medical aid and emergency response for global disasters. So when a disaster happens, they normally will send the staffs over on site and provide the medical aid support. And taking hurricanes as an example, so as a hurricane forms and moves toward the coast, decision makers need critical and real-time information, like what is happening now and what has happened here before, and to whom this is happening, how many people are affected, and who are the most vulnerable populations. So, and also when a hurricane strikes, it's not just about the wind damage. Cascading disasters often follow. And so, like a flooding or heavy rainfall or storm surge. And to address this cascading effects, decision makers also need to know what are the health risks. So, are there high risk for outbreak of infectious diseases? And also, who are the people in critical needs of medical supplies to assist these vulnerable populations? So these are the type of questions we aim to answer with our tool. And to answer this question, we collected relevant data to populate the knowledge graph. So for example, the health profiles and relevant informations are sourced from CDC and also University of Wisconsin's Population Health Institute. And we also acquired the disaster impact data, including damage information from past disasters from NOAA. And we also obtained like the forecasting zone information from National Weather Service, and also gathered the expert and expertise data by crawling and extracting relevant information from publications we derived from Semantic Scholar. And here is a more technical view of the part of the graph to support the humanitarian aid and the disaster response. So this is a very modular design. This is a storm track ontology, shows the physical information about the hurricane, like where it is located at what time, what are the wind speed, and other physical informations. And this health index ontology provides the information about the health profile of the disaster affected region. And this disaster expert ontology provides who are the experts having the relevant expertise at both local and the national scale. And the disaster impact ontology give us the previous disaster impact information, like the damage caused by disasters in terms of infrastructure damage and also number of deaths. And all of this modularized information was linked based on location. So that's why how we enable the graph to know where. And here I want to show you the GeoGraph with tools that we developed leverage the backend knowledge graph to support disaster response. So as you can see here, these dots shows the 10 deadliest hurricane that has hit the US East Coast in the past 150 years. And we can ask the question about what are the consequence impact. And these tools can also support visualization Like we can see as the hurricane is moving, what are the impact reports on the ground? So this is a combination of 3D and 2D visualization. And these different dots on the map shows the impact caused by the cascading disasters like high wind, flash flood information. And we can also click a dot to see more detailed information about this disaster impact. And we also provide another views to help build the social, economic, and health profile of the disaster affected regions. So for example, this is Hurricane Harvey, which hit the US East Coast in 2017. And what this is showing is a property damage, total property damage caused per county by Hurricane Harvey. And we can also see the public health related information. And we can also do a scatter plot, which shows which region has suffered from high property damage and also high health risk. And these counties, which are shown on the map, are probably the communities which are more vulnerable and needs the response expert to put more efforts to support the people there. So in this project, what we demonstrated is how to utilize a spatial knowledge graph and a geographic visualization tools to support fast and forward-thinking decision-making during emerging crises. And where does GeoAI help in this project? What we did is we use AI to support some automated graph generation, and this is another big part of AI. So AI's two big branch is for image analysis and computer vision, and the other big branch is more generative AI and natural language processing. So this Novel Graph project falls under the pillar of natural language processing and the generative AI. And in addition, we also develop a deep learning approach to perform a graph reasoning on top of our data to discover more hidden relationships among the dataset. And our GeoAI and the knowledge graph solutions has greatly enhanced the efficiency of our partners who often need to piece together data from public sources, which is a very time-consuming process. And then by linking the cross-domain data in a predefined way, this can help to accelerate the decision-making process significantly. And this project shows another powerful real-world challenge that GeoAI can help to address. And to quickly recap, I introduced the two recent projects, the Permafrost Discovery Gateway and the Novel Graph. And both have a shared vision to use new tools and techniques like GeoAI to bridge the gap between data and science and actionable solutions. And the success of this project really relies on a team science approach. Tackling these complex societal problems requires the interdisciplinary teams with diverse background, perspectives, and a willingness to collaborate openly. And GeoAI researchers serve as the important translators between AI and science. So we work in both directions by translating AI for science and also science for AI. And this dual role enable us to develop stronger models to better address domain-specific challenges. And looking forward, I think there are several important challenges to address for us as a community. So for example, a lot of the current GeoAI research for earth and environmental science, we mostly focus on addressing the model accuracy, prediction accuracy. But what about its solution trustworthiness? So to deploy our AI solutions in the real world scenarios like a disaster response, the solution's trustworthiness is a critical factor. And also, is there a way for us to operationalize the GeoAI research framework that can help us better evaluate, foster, and advance responsible GeoAI research? Because the GeoAI research, as we know, they will cost a lot of the computing powers, and these will inevitably increase the energy use. So as we use the GeoAI to solve some problems, are we also creating some other issues like economic cost or environmental sustainability? So those are really the factors that we need to consider when we build the GeoAI models. Is often the bigger the model is, the better for the problems. I think these kind of questions may require us as a community to discuss and really think deeper about to balance between its advances and also its potential negative impact to the community. And also, how can we continue to enhance the real world impact of GeoAI? Because the two projects I introduced is we try to develop cutting edge AI methods to not only advance science to generate important scientific information, but also to help the communities and help decision makers to really support the communities in terms of adapting the changing environmental issues. So in the future, I'm hoping that we can also, as a community, to develop a more effective GeoAI approach to further advance their real-world impact. Okay, so I will stop here and I'd be very happy to answer any questions. And before that, I would like to say a few thanks to. First, I would like to thank the AGU College of Fellows Distinguished Lecture Series to allow us to share our research with the broader communities and researchers across the world. And I would also like to thank different government agencies to support our research in AI for Earth science. Thank you.
You are mute, Julio.
Hello. Hi. Can you hear me now? Thank you, Dr. Lee, for your presentation. And you open many branches here for discussion and for, I think it opens many questions from the perspective of our job in earth sciences. We have some colleagues here that can contribute with some questions, but I want to start with a question about the potential that we have, since these lectures are for young researchers and students to engage in earth sciences. If there would be some words from you on the idea of what could be the next step for young researchers, for the students that are starting engaging in earth sciences, based on these kinds of developments that you are providing or showing today. What do you see? What do you think will happen, and what will be the future for studies?
Yeah, that's a great question. I think taking more AI classes, I think the education side is very important because we are getting into a faster developing world of AI technologies. And a lot of the, as far as I know, traditional earth and environmental science department does not offer an AI course as part of their training to our students. So how can we develop or innovate our curriculum to include the AI training, AI and the big data and computing training to our students? I think that will becomes quite critical. So in the US, I think this is also one of the challenge, like a lot of the programs are facing. So what we did recently is we received an NSF funded project called Cyber Training. So we are developing this Cyber 2A program called Cyber Infrastructure to provide the AI training for Arctic communities, but it can certainly expand to all of the geoscience communities. So we develop the in-person workshops, and we also developed a lot of the online training activities and training materials to help interested researchers and students to get more knowledge about how we can leverage AI and the big data to solve important earth and environmental science problems. So I think providing the training to the students in the earth and the geoscience programs and building a community that encouraging them to get into this new knowledge because they have a lot of in-depth training in the domain in terms of the problems. So once they know the problems and then they get to know more about on the technology side, so they will become the people who can bridge the interdisciplinary gap about using cutting edge technology to solve critical earth science problems.
Thank you. And I think also maybe grasping again the basics of all the earth sciences is still very important. As you mentioned, the models are good, but they are not as good as maybe, I mean, they're not giving the full answer to the problems. So we still need to rely on good. The basics should be clear also for students, and the studies on the real nature of problems. It's also, I think, it's very important to keep in mind at this point. Given the benefits of these technologies, but at the same time the need for the deep understanding of what is happening, what is going on in the real field. One of my one of the colleagues here is asking. He's not present here, but I want to just read the question. It says. He's Juan Camilo Villegas. He's from our department. He says his main questions relate to quality control of both processes and results from AI tools. Do you identify any ethical or political challenges in using these tools on decision making?
Oh, that's a good question. I think there are a lot of challenges presented. So here I presented two types of AI project. So the first one, the permafrost discovery gateway, is using AI for analyze satellite imageries and identify important changes on the Earth's surface. So those are kind of more a deterministic problems, which means we are extracting existing information from the data set. So the model itself is not generative, which means it's not generating something which may not be there. Yes, the model prediction may be wrong, but it will not fake something. So from that end, in terms of using AI for deterministic task, I think the ethical concerns will be less. But of course, we really need to be mindful about like some of the satellite imageries may cover sensitive areas, like the indigenous land, which they may or may not be comfortable of like showing all these satellite imageries. So we want to make sure that those sensitive information are not included. And also in a lot of the satellite image analysis, we also pinpoint the locations. So if there are sensitive location sensitive data, we should also remove that from our analysis. So those are the ethical concerns related to using AI for analyze big data to do deterministic tasks like extracting information. And on the other hand, the second project, which like we use a lot of the large language models for doing natural language processing, I think that will create a lot of potential discussions in terms of are we properly protecting the information source? Like a lot of the information we are analyzing, is that okay to be put into large language models to do the analysis? Of course, for ChatGPT, what we are using is we are using an enterprise version, which will protect the data privacy. Means that the input data will not be released and shared and used for model training. So that kind of protecting some of the data privacy, but not at a very strict level. And another thing is generative AIs could always generating something that is not true. So in that case, how can we accurately curate this information? So we did right now developing the tools for like disaster response and develop real-time situational awareness. So we need to be really carefully curating our data, the data set that we generated by the help of large language models, because without these layers of validation, it's very difficult to make sure that the data, yes, large language models can help us accelerate a lot of tasks, but we really need to have rigorous review process to make sure that they do not incorporate like some misinformation or false information. This is really critical because in high-stake decision makings, if we are providing the decision makers with some fake information, that may affect a lot of the people. So these are, I think, as we see the advances that the technology can bring us, there are like a set of a larger set of the questions that we really need to be incorporate into our research to make sure that our result and our solution is trustworthy.
Thank you, Dr. Lee. We have a colleague here in the meeting as well, Dr. Arias, Paola Arias. So if she wants to ask a question, please, you can join us now.
Thanks a lot for your presentation. I have a question, but it's more general. It's not only like regarding the particular applications you have shown with artificial intelligence, and it's also related with Juan Camilo's question regarding the ethics. Like, what do you see are the huge challenges we are facing as humanity, but also I will say the young generations in terms of artificial intelligence being a tool, but somehow being used not necessarily with human intelligence, you know? So like this is a huge challenge, an ethical challenge we are facing. It's not only for earth sciences, but in general. Also, if you are considering author rights, for instance, etc. So what do you see regarding the challenges in ethical values using AI?
Yeah, I think there are a lot of challenges, and so thank you for your question. I think this is like one of my biggest concern and worry as well, and also a topic that I often debate with my own team and my students. So I'm seeing a trend is like the students are incorporating AI very intensively in their research process. So, for example, they may ask like AI has becoming one of their collaborators about, hey, helping me find some literature and helping me answer these questions I have. So, and also helping me do some coding. So I want to develop semantic segmentation tools for image analysis. Can you help me to generate some code? So these are all great help, but at the same time, if our next generation of students are heavily relying on AI to do the task for us, then we may not be able to go through the rigorous training process that prior to AI that we have received. So we know all the science, we know all the technologies, so we know how to do coding. But if we lose that capability, how can we make sure that we have the knowledge above AI, which can help to validate whether the AI generated code, for example, yes, it can run, but will it generate some potential errors, and whether it's run correctly? So those are all the type of questions. So if we are heavily relying on AI, are we losing the proper training for us to really gain the critical spatial and the critical computational thinking skills? So those are the things that I think I'm still debating about how can I provide the training to my graduate students to make sure that they gain all the needed knowledge and skills, and at the same time not to lose their capabilities to AI.
Thank you, Dr. Lee. I was surfing through your nowhere graph while you were talking, and I wonder if it's currently available for people to surf that website or the graph. It's only for the United States at this point, or it covers several places in the world with data from the U.S. agencies. What is the vision for that website? Can people use it openly?
Yeah, well, that's a good question. This project actually have ended, but I think we should be able to having the open endpoint available, which you can get access to the actual graph data. And in this link, we are also providing the GeoGraph with systems, which allows you to interact with our system. So I think I need to make sure maybe there's like HTTPS with this link. So the geograph viz system is up and running on my lab's website, so that should be able to get public access. And yes, right now, almost all of the data set are US focused. So we obtain the public information from different US agencies. And one of the follow-up activity for this project is we are adapting the visualization tools as well as the graph technology empowered by large language models to support the disaster response in Arizona. So we are collaborating with the Arizona Department of Emergency and Military Affairs of trying to use our technology to help Arizonians to mitigate the effect of disasters like wildfire, extreme heat, flooding, and other kinds. So pretty soon we should have another working prototype available centered on Arizona. But the technology is open source. So if you want to adapt these similar tools and technology to a different region, it's highly possible.
I know that many things work with projects in general, and you have some funding to do projects, and you have students working on those projects. But in terms, for example, of collaboration with universities like our university, let's say, where we have, I think we have the skills and we have the people, we have students that are very, that we can motivate to work in this kind of tools and ideas. How can we maybe think of collaboration that is possible, but at the same time, it doesn't require as much as big projects and funding to work on these issues? What do you think we can do? Or
yeah, I think this is a great question. We are definitely open to collaborate in terms of how we can work together, like a lot of the tools that and also data set we developed from our lab and also our collaboration are open source. So which means that can be easily adapted for broader applications. And if there's any specific collaboration opportunities, for example, if you are interested in Noir graph or interested in our AI for image analysis capabilities, I think we can definitely do a follow-up call and to discuss what is the best way of moving forward.
what do you know any of the competing, let's say, works on this area? For example, that I'm thinking of the organics of the way you proceed to create the whole web and the whole idea. And I suppose there is still of a human input on the structure of the cyber infrastructure that you are developing. So how much of that infrastructure is, let's say, research based on the person that is doing the research, and how much is really something that is logically structured that can be applied everywhere, or it has room for, let's say, creations that are proper of each place to develop in a different way?
Yeah, I think this is a really good question. In a lot of the tools that my team has, I demonstrated the geograph with, and there are also other cyber infrastructure tool my team has developed. For this specific visualization tool to support disaster response, we collaborative a lot with our like direct relief, which are kind of the team that to provide the relief expert. So we really I really value the co-design process. So from the need perspectives, so they will show us, okay, these are the important data set we will be looking at when a disaster happens. So then we are trying to use our technology to collect this data and integrate them together and develop tools to support. But of course, in the like for the web-based tools or cyber infrastructure, how user and the computer can interface together. What are the interactions? I think that will require a lot of these unique designs and also from our past experience. So I think in terms of the data set and how the data are integrated together, those are definitely could generalize. Maybe slightly tailored based on different application needs. In terms of the interaction, human and computer interaction, that will be based on needs and also based on our like own research perspective. So yeah, so based on different needs and the different project needs, that part probably needs to be adapted and change a little bit. But you see the entire workflow, right? You see the driving factors for us doing this because we know these are the important data set, and we want to know where are the expert and expertise are located locally and globally. And we want to identify the vulnerable communities. So those are the information we are trying to incorporate. And how you are leading your audience to get your answer step by step. So I think each of the different team may have slightly different way of solving that. I think the best that tailor to the actual decision process through a co-design process would be, I think, very valuable.
Thank you. I don't know if Professor Paola has another question for Dr. Lee.
No, I don't.
Perfect. I just want to finish with one question, which I was wondering when I saw when you were explaining the web and the knowledge, the nowhere, all the institutions that provide information. What about newspapers, local newspapers and information that you get? Is that part of the nowhere strategy, or would be? I think it's a very important source of information for disasters, for actions that occur everywhere. So
this is an excellent question. Yeah, so right now we only have integrated like a structured data from government agencies, and also we extract expert and expertise information from publications. We haven't incorporated the news report yet, but as I mentioned in our current project that's expanding and readapting this work to help Arizona's, we are actually incorporating some local news. As you mentioned, those provide really important real-time information. So for example, we are following the local news, like in Phoenix, reporting a wildfire. So they will say, okay, so from this date to this date, there's a road closure. And then after a couple of days, the news report were updated, then showing this road is reopened again. So the change of the status of the like how important lifelines and the critical infrastructure are being affected is actually contained in the news report. And after a number of days, when they reopen again, so I think those of the lifeline impact to the lifeline and the recovery of the lifeline, those information are very important to our collaborators and the disaster response expert, which are included in the local news with a real-time factor. So those, I think, is a very important data source for us to consider and also integrate, especially from developing the situational awareness perspective, because we want to show what is happening now after the disaster. Well, thank you for the suggestion.
Perfect. Thank you, Dr. Lee, for your presentation. We reached the hour, so we want to be very committed to the time that is provided for the lecture in AGU. And again, thank you very much for being here, Dr. Lee, for your presentation. For us as colleagues in other country, and the program or the idea of this distinguished lecture series for us is very important. We have participated for the last 3 years, and we hope to continue to participate in the future series. So thank you, AGU, for also trusting these opportunities for the universities to host conferences like this around the world. I know that there are many others circulating or occurring right now in different parts of the world. So thank you for being here today. And for all the people that is watching this video in the streaming or later recorded, we're going to provide a link for a poll. It's just a little survey for people to answer a couple questions about the experience that they have with these lectures, which is something that AGU requires for also making statistics of the use and importance of these lectures. So thank you very much, everyone. And with this, we finish the presentation. Thank you.
Thank you for having